This is chapter 23, example 2. This is a seemingly straightforward problem, essentially a 3-bit counter. And so we know how wide the output is. It counts either an odd or counts in binary, but it's either odd or even based on an external input. So the external input is even. When it's asserted, it counts even. When it's not asserted, it counts odd. So that's pretty straightforward. Essentially what we see from that is no decoder necessary, no output decoder necessary, at least for the count, because it's a 3-bit counter and we're not modifying the count in any way. But what we're doing is we're putting qualifications on how it does count based on that even input, and so that's going to be an issue. So let's go ahead and draw the interface to this problem. There's a couple different ways to do this. The important part is when you think this out, and honestly, I missed this the first time. That's why I started over on this problem. It's the RCO. The RCO is, well, it's a ripple carry out. It's asserted when, and it's an up counter. It's asserted when the device has hit its terminal count. This terminal count is based on the even input. The even is asserted, meaning it's counted up in even. 6 is the terminal count. If it's counting up, if even's not asserted, it's counting up an odd, then the terminal count, 7's the terminal count, and RCO turns on. So essentially the RCO is based on whether the even is asserted or not. So what we have here is an output decoder that's going to be based on that input. So which essentially means RCO is immediately output. The count itself is a more output since it's only dependent upon state. So there's a couple different ways to do this. I'm going to take a shortcut on it and kind of violate some rules that I told you. But the first thing we want to do here is draw the state diagram. It's going to take a second because by all means there's 8 states. So let's get started on that. There's the rough state diagram, shows all 8 states. What next thing we need is transitions in this thing. So the transitions are kind of funny. We'll go ahead and do this kind of a shortcut way. If I'm in 0 and it goes to 1, that is because the even is turned off, which is counting an odd. And so this is going to be kind of go back and forth on this thing. Okay, if I'm in 1 and I go to 2, that's because the even's turned on. Okay, and you can see a pattern developing here. There is half of my transitions. Now the other half are going to be a little bit different here. Essentially I need 2 transitions from each state. So if I'm in 0 and even is turned on, I go to 2. If I'm in 1 and even's turned off, I go to 3. If I'm in 2 and even's turned, so I got it off, even's turned on, go to 4. If I'm in 3 and even's turned off, I go to 5. I hope you're seeing the pattern here. If I'm in 4, even's turned on. If I'm in 5 and even's turned off, I go to 7. So if I'm in 6 and even's turned on, I go to 0. If I'm in 7 and even is turned, here I have even turned on, even's turned off. Yes, that's going to be a problem. So that's pretty good now. Now the last thing I need to do in the state diagram is handle the RCO. Now RCO, it's always going to be off, except in these 2 states. This is what I need to worry about. So in these first 6 states, it's not dependent upon the input. In the last 2 states, it is, and I'll figure that out when I get there. So I'm going to put it in here. There it is in those states. Now in the final 2 states, RCO is based on the input. And so therefore I can't put it in the states. Now the general rule is If it's a more output, you put it in the state, otherwise you can't put it in the state because it's a Mealy output. But what I'm doing here is saying in these 6 states, this RCO is acting like a more output, so I left it in the states. It makes the diagram a little bit neater, and by all means this diagram is in desperate need of neatness here. Now, so lastly, let's kind of reason this thing out. If I'm in state 6 and even's turned on, RCO turns on. If I'm in state 6 and even's turned off, which is right here, RCO's turned off. Okay, so we can do the same thing for this other state here. It's going to be kind of messy. So I'm in state 7, it's even's turned on, so it's not, state 7 is not the terminal count, so RCO is off, which means right here RCO is on. Okay, so this is very messy. Should have made it bigger, but I didn't really have that much room. That's my great excuse here. RCO is a Mealy output, but in the first 6 states, it acts like a more output because it doesn't change in those states. It's only in the last 2 states that the RCO acts like a Mealy output and is a function of the input. And that's how we list it in the diagram here, and I'm going to call that done. Next thing, we'll draw the circuit diagram. Output count is essentially the output from the state registers, while the RCO is a function of both state and the input, which we have here, and so that makes it a Mealy output. And so next thing we need to do is the PSNS table. So this is going to be long and ugly, so let's do it. Once again, we're combining the 2 tables for the output decoder and next state decoder. I actually didn't feel like writing this, so I made these decimal, which is not a big deal. What we notice is they do come in pairs here, which we've seen many times before. We didn't have to structure the table like that, but it makes it much easier. So I'm in state 0 and evens is 0, I go to state 1. I'm in state 0, evens of 1, I go to 2. Okay, I'm in state 1, evens is 0, I go to 3. I'm in state 1, evens of 1, I go to 2. This is the thinking behind this. I'm going to go through this without speaking it and hopefully not make a mistake on this one. Looking through this, and I think it's right, but I see a pattern there. I see the same pattern developing, like the 2 repeated values in the same spot, and that's indicative that some things must be right in this thing. So the RCO in the circuit is always 0, except in those final 2 states when I have to be careful with it. So I'm in state 6 and the evens turned off. That's not the terminal count for an odd, and so that's a 0. But if I'm in state 6 and the even's turned on, 6 is the terminal count for an even. 7, if I'm in state 7 and the even's turned off, that is the terminal count. If I'm in state 7, counting the even direction, that is no longer the terminal count. So the terminal count for the even direction is 6. So that's a 0. This is essentially done. It could have been a little bit more neater on this guy, but we're kind of limited space here. And I'm going to call this problem done. Once again, the highlights are, there's not a real hard, fast rule of what to do with the Mealy and more outputs. Since the RCO is a Mealy output, I could have listed them with all the inputs. That would have made the state diagram really messy. So I opted to take 6 of those states, put the RCO in it, because in those 6 states, RCO doesn't matter what the input is. It's always 0. The RCO is always 0, independent of the even input. So it's these final 2 states where even matters, and we're going to call this one done. You can see that same thing here. This is the state for 6, this is the state for 7. Notice that the RCO changes in the middle of those states, or it can change, which is a characteristic of a Mealy output.